Good afternoon to all of you. So I welcome you all to this first live session for the course Computational Fluid Dynamics for Incompressible Flows. So if you have any questions, you please post it here. In the meantime, I will discuss some questions already posted in the Excel file. So one question was there that initial conditions are used only for marching problems. Yes, you have marching problems. Then say if it is marching in time, then you need to specify the values of any variable at time t is equal to 0, right? At time t is equal to 0. So that is your initial condition. So for marching problems, you need to initialize the value at time t is equal to 0. Similarly, if you have some marching problems like boundary layer equations, okay, so if you are solving the boundary layer equations and steady boundary layer equations, then obviously it will march in x direction. Okay, so at x equal to 0, you have to give the value of the variables. Next question. Next question, in von Neumann stability analysis, it is mentioned that boundary conditions are periodic. What does it mean? If the boundary values are fixed, will this analysis be applicable? How do you justify a periodic function or error? For error, Fourier expansion is applicable only for periodic functions. How do you justify this applicability for finite difference equations? So if you remember, when we actually discussed about the von Neumann stability analysis, we told that boundary conditions are periodic. So the first question is that what is periodic boundary conditions? So let us say that you have a flow of fluid flow over, say, inline cylinders. Okay, there are many inline cylinders like this, and separated by same distance in the axial direction as well as in a particular distance in transverse direction, like this. Okay, and there are many such cylinder arrangement. So if you take one such block, okay, so what we can do, say, instead of solving, say, this full domain, we can take up to know what fluid flow is happening behind this circular cylinder. We can take, say, one unit of this, and if one unit of this if we take, then you can see that it is like everywhere the same fluid flow is taking place. That means, say, whatever is coming in here, okay, or whatever is going out from this domain, it is just inlet of this, right? So whatever flow is going out of this first domain, that is the inlet of second domain. So that means whatever flow is going out, so that is coming in for the same domain. So you can see it is repeated, right? So that means it is periodic in axial direction. So this is known as periodic boundary conditions. Now when we did this von Neumann stability analysis, although we assume that boundary conditions are periodic, but when we solve some finite domain problem, then obviously the question is that whether this is applicable or not. Yes, it is applicable, because say if you solve some problem using, say, periodic boundary conditions, if, say, from von Neumann stability analysis, let us say delta t, if it is restricted, let us say delta t is restricted by, let us say, 0.002. Okay, So delta t is restricted by 0.002. Now original problem, whatever, although it is not a periodic boundary conditions, then you will get maybe delta t is less than 0.001. So you can see that this using the periodic boundary condition, although it is 0.002, but for your original problem which is not periodic but we assumed somehow that this is applicable, then it is delta t is restricted by 0.001, which is lesser than anyway 0.002. So anyway this criteria will work for your domain. So that means it is applicable also in non-periodic domain. But if you use periodic, maybe you can say that delta t is much larger. Okay, so that is the difference. So it is applicable. Next question: what will be the type of questions in the final exam? Will it be like the assignments or will it be derivation 2 like class lecture? No, it will be like assignment problems. So in the final exams you will have total total 50 questions. Okay, so each mark 2, so there will be 100 marks and you have to solve within 3 hours, and it will be assignment like questions. Few questions maybe will be remembering type, okay, or you can solve within a 15-second or half 30-second, but some problem you need to derive and write the see the final answer, so it might take some time, but overall time you means within 3 hours you will be able to complete. Next question is that related to the exam center. Okay, so you please send email to the NPTEL team of IIT Madras, and you check, because this I do not know where are the centers actually last time, but obviously IIT Madras NPTEL team will be able to help you. Next question is that I am first year student in PhD physical science, and my work will involve particle aerosol deposition in lung using CFD. My query is, what are the best software available for CFD? I heard the names like OpenFOAM or Salom. How to choose a particular software? Is there any coursework available on them? So as we have discussed in the introductory lectures of this course, that there are many commercial softwares available, but it depends on that which type of problem you are going to solve, whether it involves multi-physics. So OpenFOAM is open source software. Okay, it is finite volume based software. So you need some kind of coding experience because you need to write some code when you are using OpenFOAM for your problem. And Salom is the grid generation software. Okay, but anyway, in the OpenFOAM you will get you will get the grid as well, and there are many other commercial software like ANSYS Fluent, then Console is a very good multi-physics problem. So if you are solving any two-dimensional problem, then it is very good. Otherwise, if you are solving for three-dimensional with higher grid, then in the console it takes more memories. But if only this particle and aerosol deposition in lung if you are going to solve, then obviously it will be, I think, complicated geometry. So you need to generate some unstructured grid, and you will be able to solve using OpenFOAM because it is a very good finite volume open source software. However, there are no course available, but there are many tutorials available in their respective software this web page. as well as in YouTube. So you just search and find some tutorials related to your problem. Okay, whatever you are planning to solve. So you just search and try to solve some example problem related to those physics which you are going to solve. So now next question is, what do you think in the is the future of CFD? Are there any current developments in the field? Is the field becoming saturated? So obviously, this computational fluid dynamics, there are many aspects to look into, different algorithms to look into. So although you can see that CFD in general, finite difference, finite volume, maybe for general uh, solving for Navier-Stokes equation, maybe it is very simple you are thinking, and it is very maybe you are telling that it is saturated, but say multi-physics problem which were not attempted earlier. Okay, so now in the CFD there are many advancement, okay, in solving the multi-physics problem. Okay, so and also very complicated industrial problem. So we cannot say that it is already saturated. And in addition, from CFD data, now you can use obviously this machine learning, okay, to solve some problems. So now there are many applications of this machine learning in CFD. Next. So there are some question that can you please explain in assignment 3, question number 4, graph 1. Why this is, you can see in the logarithmic graph of truncation error versus grid size 1 and 2 respectively represent central difference and forward difference. Okay, so how this A is correct. Okay, so you can see that in central difference the error, okay, varies as delta x square because second order accurate, and in first order point obviously the error varies as delta x. So you can see that if you take the logarithmic scale, the slope for central difference scheme will be greater than the slope of the forward difference scheme. So hence the correct answer is A. Yes, another doubt was there. The question number 10 in the assignment number 5 needs explanation, correction. The temperature is asked for, the answer are given in the second. Yes, so I think there is some mistake while giving the answers. Okay, so the answer will be in degree centigrade only. Okay, and this is the answer. So can you show the slide of this von Neumann stability analysis, or because one student asked that whatever wrote was not visible, so your all is not 100% clear. Okay, so in the von Neumann stability analysis, I think you please show it once again, this PPT. Yes, but it is not visible totally, the upper side. Okay, so I will just paste. Okay. So I am just writing here. So about the von Neumann stability analysis, whatever I discussed about the periodic boundary conditions. So I was telling that if there are say circular cylinders placed in a inline manner having same distance between two cylinders, then what you can do, that instead of solving the same problem to know the flow physics, you can just take up one unit of this cylinder. Now you can see, if this is the 1 and this is the 2, then you can see whatever is flow is going out, that is the flow coming in. Okay, so you have to choose the boundary such a way that it will be in the middle of these two cylinders. So obviously whatever flow is going out, that will be flow coming in. And actually for this geometry, so whatever flow is going out, that will be flow coming in. So this is your periodic boundary condition. So instead of solving this problem, if you solve this one unit of this, obviously you will be able to understand what is the flow physics. So in this, this is known as periodic boundary condition. And already I have discussed that if delta t, if you using real periodic boundary condition, if you use the von Neumann stability analysis, maybe whatever time you will get. But if it is for your actual problem which is not periodic, but you are using von Neumann stability as analysis, the time restriction will be the lesser than that. So obviously it is applicable. So another question is that, sir, I am in second year of mechanical engineering. What are the prerequisites for me to understand the course best? So if you are a second year mechanical student, then obviously you need to have the knowledge of fluid mechanics. Okay, at least fluid mechanics and heat transfer. Okay, so then obviously whatever equations you are learning in the fluid mechanics, so that we are discretizing using numerical analysis. Okay, so that is your CFD. So obviously you should have proper knowledge of fluid mechanics and heat transfer. Okay. If there are any more questions, you please post it here. So next question is that regarding the machine learning. Okay. So you please do some machine learning course, okay, available in this NPTEL or Coursera, and obviously whatever CFD data set you have for a certain problem, okay, so using machine learning you can feed those data, and obviously it will try to replicate for any problem, okay, using its own intelligence. So obviously that way you can actually use machine learning in CFD. So you can see that to solve any problem, obviously in the using CFD you need to have sufficient refined mesh, and for that obviously you have some computational cost. But if you use machine learning, then if you feed the data, so obviously it will take less time than whatever numerically you are solving for the problem. Okay, so if you have any other questions, you can post it in the discussion forum. Okay, we will answer, and again we will meet in the second live session. Thank you very much.